Can you see the screen?
Yes, sir.
Okay. So these are the features of this Darlington pair. We'll call it BJT Darlington pair. So this has 3 terminals like any other transistor, right? And these 2 transistors together, they work like one single transistor. And they can be considered as one single transistor. And this one Darlington pair, like any other transistor, not only common collector, we can also use this in other configurations like common base or common emitter. In all 3 configurations, we can use Darlington pair. So today we'll show first an interesting modification of this Darlington pair circuit. So what we have done here,
So replaced the BJT with a MOSFET.
right, we replace the BJT, the first transistor, with a MOSFET. So what difference it would make?
Mm. So it is a voltage control device. So, but has high impedance, high input impedance.
This is the gate, and what the gate current here? How much is the gate current? Gate is that isolated, what is known as the channel, is an insulation. So gate current is always zero uh, for MOSFET. So because the current is zero, the input resistance of the MOSFET is considered to be infinite. Right? So by replacing the first transistor with a MOSFET, we can achieve the infinite input resistance. So that is a feature of an ideal voltage buffer. So that is one step closer to the features of an ideal voltage buffer. By replacing the transistor with a MOSFET, right, we can achieve one of the features of the ideal voltage buffer. This is known as the BiCMOS or the BiCMOS. BiCMOS Darlington. Darlington. This is our BJT, the bipolar junction transistor Darlington pair. This is BiCMOS. Here, bi stands for bipolar, right? And that refers to the transistor, the BJT, bipolar junction transistor. CMOS refers to this MOSFET, and so together they are called BiCMOS Darlington pair. So this is also represented. So that's the actual circuit, and this is the emitter. So that's the circuit symbol. Circuit symbol of BiCMOS Darlington pair. It's also known as the composite transistor. two different types of transistors, BJT MOSFET together combined, right? They are working like one single transistor. It's also known as the composite transistor. The voltage here is VGE, that is gate to emitter, right? And that VGE will be, here we have VGS, that is gate to source, and then we have VDE. So this together is our VG. So VG is, we have VGS plus VG. Any question, guys? So input resistance is infinite. If you are looking from here, so that will be the output resistance. How much is the output resistance in this case?
Low. Low output resistance.
No output resistance, why?
Because we're looking from the emitter side and we have only R pi resistance.
From emitter side, but don't we have resistance here? From emitter to base?
That is R pi.
R pi looking from the emitter?
Sir, R
R pi into beta plus 1.
Looking from the emitter side?
sir, it's R
R pi.
Looking from the emitter side is R pi?
R pi divided by beta plus 1.
R pi divided by beta plus 1. What is that?
Resistance reflection moment that R pi is reflected onto the emitter side.
It seems like you have again forgotten some of the basic things. Okay, so let's say the resistance here, we call it R naught prime. Okay, so we can write R naught is equal to small RD, RD2, and plus R naught prime divided by beta plus 1. Does that make sense?
Yes, sir.
Now, what is R naught prime? Right? What is this R naught prime? Any idea? For common emitter, it is small RE. Sorry, for transistor bipolar junction is small RE. Right? If you look from the emitter. Now, what's the equivalent resistance for the MOSFET looking from the source side? Right? They're kind of the similarities. Right? So, to understand what will be the resistance there, so we need to take a look at the pi model and the T model for the MOSFET. So that is our gate, and that is our source, that is our Oh my gosh. That is our drain, no? I don't know. And that is our source. Okay, so that is our voltage VGS, this plus and minus. It is equivalent or VBE for bipolar transistor. So here the gate is open, right? And this, so at the input side, why it is open? Because the input current is zero. There is no current flowing. So it is infinite input resistance, gate is open here. And the current here will be GM VGS. So that is the current that is flowing into the source from drain. And resistance here is R0. So it looks similar to what we have for the transistor, the bipolar junction transistor. We have same structure, but here we have R pi. That's the only difference. Otherwise, everything is similar. Now the T model. What is the T model? T model looks like this. So we have a so that is our drain. This is our gate. Now this is our source. The current here is the source current. The current here is our drain current. Right? So for the MOSFET ID is IS, right? Because the IG is zero, right? There is no gate current. So this current must be equal to this current. These two currents are same. This is the difference with the bipolar junction transistor where IC is alpha IE. So there's a parameter alpha, but we don't have alpha here. So that's one difference. And here the resistance, what the resistance is given by 1 over GM. What we had for the transistor RE, we have GM between gate and source. Now, how do we get this GM? As you look, if we look at this model here, right? So the pi model shows infinite, but in T model, we see a resistance of 1 over Gm. Why is this difference, right? Why it is not open here? Because we are looking from the source side. I mean, this is here, right? You are looking from the source, and when you're looking from the source, there's a current flowing here, right? That is our source current. The current is not zero. If the current is not zero, then I mean, resistance cannot be zero. Resistance cannot be infinite, right? As long as you have a finite current flowing, you will have a finite resistance, right? If current is zero, only it is infinite. If you're looking from the gate, current is zero, but if you are looking from the source, current is not zero. So that means if you are looking from the source side, the resistance between the source and gate is not infinite. So what's the resistance then? If you're looking from the source side, so then R0 prime we can write the voltage between gate and source is VGS, and that divided by IS. Right? So that will be the resistance. So that is definition. Voltage divided by current. So looking from the source side, source current is IS, and voltage between gate and source is VGS. So that's the simple application of the Ohm's law. So we have VGS. We keep it as it is, VGS, and IS is the source current, which if you look at in the pi model is GM VGS, right? The current that is flowing, and the ID or IS, that is GM VGS. So if you substitute that for IS, we have GM VGS, VGS and VGS will cancel out, and you end up with 1 over Gm. So that will be the resistance looking into the, if you are looking into the source of the MOSFET, which is 1 over Gm. So then the output resistance we can express as small Re2 plus 1 over Gm. Here it will be Gm1 or Q1, that divided by beta 2 plus 1. So that will be our output resistance, and we see that output resistance will be also very low because 1 over Gm is low, and that we are dividing by again beta 2 plus 1, it becomes very low. So already the Re2 is also small. So if you compare with the common collector, two-stage common collector or transistor Darlington pair, probably it is even lower, because in the transistor Darling pair we have here Rs, and that will also reflect here some part of it, though it gets divided by beta 2 beta plus 1 square, right? So if you compare with the transistor, the BJT Darlington pair, the MOSFET Darlington pair has a similar, level of the output resistance. If not lower, it will be in the same range. So we can call it very low output resistance. And it has infinite input resistance. So as a voltage buffer, if you're using this, it will work. It will be a better voltage buffer, even better than the two-stage, the BJT Darlington pair, because in BJT Darlington pair, with the input resistance is very high, but not infinite. Right? Still, it is a finite input resistance. But in the MOSFET, we practically we can get an infinite input resistance, right? So that is an improvement over the BJT Darlington pair. Any question, guys? No question. So for the multi-stage amplifier configurations that we have considered, different configurations, all are considered. We all are cascade amplifier configurations. All belong to this class of cascade configurations. So now we'll consider the cascade configuration, which also has a very important role in integrated circuits, in the design of integrated circuits. The cascade amplifier plays a very important role, though it is not that much used in discrete circuits, only in the special cases. But for integrated circuit, it's a very important configuration, very important circuit block. So let's see how it looks like. So this is how it will look like. We have two transistors Q1 and Q2. So what's the configuration of Q1?
Common emitter.
Right, Q1 is in common emitter configuration. And what is the configuration of Q2?
Common base.
Right, this is common base configuration. So that is known as the cascade configuration. We can call it common emitter, common base, cascade amplifier. So now we try to determine the amplifier parameters for this circuit, starting with our input resistance. What is the input resistance? So what's the input resistance Ri?
Sir, R pi 1.
It's R pi 1. Now output resistance. What will be the output resistance?
Sir, R naught into 1 plus GM, then
R naught 1 plus
GM,
GM2, then
R pi 2 parallel R naught 1.
right, R pi 2 parallel R naught 1. Right, that is the circuit. If you look on the output side, this circuit we can simplify it like this. That is base is grounded. That is our Q2, right? And then from here, this whole part we can replace by the resistance that we have here. That is small r01. Looking down, right? So you see the resistance of small r01. So that these two circuits are equivalent as long as this Q2 is concerned, right? With respect to Q2, if you just connect a resistance R01, it will feel the same, right? So the resistance that you are looking from here, the output resistance R0. So that's the structure that we discussed before, the output resistance of this transistor with a resistance in the emitter, right? So that will have this expression. The small r0 to the output resistance of Q2, that will be multiplied by this factor. If you are grounded, it will be just small r0, but if you have a resistance in the emitter, then we have this multiplication factor here, 1 plus GM times this R pi 2, that's resistance here, in parallel with this R0 1, that's in the emitter. Okay, so that's correct. That's our output resistance. Now this we can simplify a little bit because why we can simplify this one, because you see that R0, the output resistance of the transistor, is usually much larger than R pi, right? R0 is in the range of hundreds of kilo ohm, right? And R pi few kilo ohm, right? Usually around 2, 3 or around this range. While you R0 you can have usually higher than 50 kilo ohm, around 100 kilo ohm. Usually much greater than this small R pi. So then this output resistance we can approximate to, we have R02 times that we can replace by GM2 and R pi 2. So this parallel combination will reduce to the just R pi 2, maybe this smaller one. So and what is GM and R pi?
Sir, one.
One? What is one?
It's a constant.
Constant, what's that constant?
Transconductance into resistance.
See, GM is IC by PT, right? And what is R pi?
So VT by IB.
Right,
Beta.
right. So that we get beta, right? IC by IB, beta will cancel out. So we get actually beta. So this product is nothing but beta. So what we get R naught to 1 plus beta. So that will be output resistance. And you see that R naught, it is already high, we said, and that getting multiplied by 1 plus beta. So you get tremendous output resistance. If R naught is 100 kilo ohm and this is also 100, so you get 10,000 kilo ohm or 10 mega ohm, right? So that's any measure that is very, very high output resistance, right? So that is one the most significant feature of the cascode configuration. No other configuration gives you that high output resistance, right? Only the cascode configuration gives you this very high output. This, I mean, in the output resistance. The common base also gives you high output, but not that high, right? Because it's the R naught is getting multiplied by 1 plus beta, and beta is large, right? So that gives very high, very, very high output resistance. That's the main feature of the cascode configuration, and that is, wisely used. That's property is exploited in many constructing different intelligent circuits, in integrated circuit. Anyway, so that is not our focus now. Our focus is the basic operation principle of this cascode on amplifier and what are the different features. So one feature we have determined is the input resistance same as the common emitter, because the input is our common emitter configuration, and the output with the resistance we get like this, which gives us a very high output resistance. Now, what are the other features? The voltage gain and current gain, right? So voltage gain, which we can express as V naught by Vi. So that is not overall voltage gain, because overall we will have the source here. Without the source, we can add that. Let's first try to find out what is this one. So V naught by Vi, how we can determine. The easy way to find voltage gain in this situation is to determine the V naught here first. V naught we can express as I naught Ra. Right? And what is I naught, right? So here we'll have this current flowing in this direction, the collector current IC, which we can call IC2, right? The collector current of Q2. And we have current here in the emitter, that is our IE2. Right? And that IE2 will be same as what we have here, IC1, right? So I naught we can express as minus. Okay, let's change this one. So I naught we can express as minus IC2. So that will be minus IC2 Rn. Now IC2 we have to express in terms of IE2. And what we can write? IC2 in terms of IE2.
So alpha IE.
Right. So it will be alpha, this alpha IE2, alpha IE2 Rn. IE2 same as IC1. So again, we can substitute that. So we have I alpha 2 and we have IC1 and times RA. So that's it, right? Yeah. Okay. So now what we need to do, IC and we in the denominator we have the voltage, right? So IC now we express in terms of voltage. The voltage here is the base to emitter voltage VDE, right? And we use this relation that uh, the IC is GMVB, right? IC is GMVB. So this is for Q1, so maybe we can put 1 VB1. So IC1 would be GM VBE1 or GM1 VBE1. So with that, now this expression so the V naught now we replace IC1 by GM VBE1. So we have minus alpha 2 and we have GM2 and we have GM1 VBE1 and what am I writing? So GM VBE1 that times RF. And what is VB1? VB1 is?
VI.
VB1 is same as VI. Exactly. So minus alpha 2 GM1 VI RF. Okay. So V naught by VI, so VI and VI will cancel out and you will have minus alpha 2 GM1 RL. Okay. And that alpha, I mean, we can approximate to alpha 2 is close to 1, approximate to minus GM1 RL. So that is our voltage gain, right? Can you recognize this expression? Have you seen this anywhere before?
Yes, sir.
Where?
Sir. What?
Sir, the voltage gain across the base of a common emitter amplifier.
It's the same as the gain expression for the common emitter. With just one difference. What is the difference?
Minus, no, GM. So in common emitter amplifier, it was R naught parallel. GM was multiplied by R naught parallel RL. In this case,
We had the small R naught, no? The output resistance of common emitter, but in this case, we don't have that R naught, right?
yes, sir.
So this gain, the expression, the gain of this cascode is independent of the output. It is not affected by the output resistance of the transistor, right?
Yes, sir.
R naught is not having any impact here. So that is the one major difference here. It is, I mean, it has some important implications as we'll see later, but for now, that is the main difference. So we've taken note of that. And though it looks, I mean, not important, because anyway, for common emitters, what we said that R naught is much larger than RL. So we can always approximate that parallel combination to RL, making it independent of R naught, right? But that's not always the case. Sometimes we'll see that R naught will have an effect on the overall gain in some situations. And we'll encounter those situations, and in those situations, then this will be very useful. We can make the gain independent of the R naught, small R naught. So that's what we get from the cascode amplifier configuration. Input is the our common emitter, so that's our main amplifier. That is, so the gain is same as the gain of the amplifier, common emitter amplifier, but just one simple modification. We added this common base at the output of the common emitter, and we get a gain that is independent. So common in the base here basically is working like a current buffer, as we have mentioned before. The features of the common base are opposite to the features of the common collector. Like common collector has very high input resistance, common base has very low input resistance. Common collector has very low output resistance, and common base has very high output resistance, right? Common collector has unity voltage gain, common base has unity current gain. So the features are completely opposite, and these features are what we need for the current buffer. And what is a current buffer? Current buffer is like an amplifier that can transfer current from one circuit to another circuit, right, without any much impact on the overall performance. So basically, we can also show this the configuration like this. So you have the common emitter here. Then that goes, the output goes to the common base, right? And then you have the RF, right? So here you have the current of the common emitter, right? The output current for the common emitter, it goes, and you get the same current. Output current here would be same as this, right? Because that has a unity current gain. Right? So it is transferring the current to RL, right? Whole of the current is being transferred to RL. So that is the, you see that how it works, right? If we didn't have this current buffer, so what happens in case of common emitter, if you are directly connected to RL, right? Then what happens here, you have this R naught, right? Now, whatever output current you will have here, you call it R naught C. So that will divide into these two branches. You have I naught 1 and I naught 2, right? So that current will split, right? Now, when you are adding this current buffer, right? So the buffer is transferring this current, whole of the current, to this, right? Because now the current here, you still have this, but it will be very negligible current, because this input resistance here, you have very low input resistance. So most of the current will flow here instead of going into here, right? So that is how the circuit will work, and that is how it will make a difference, right? Make this difference, that output, the gain in this case will be independent of the output resistance of the component. Is that clear, guys? Any question?
Sir,
Yes.
স্যার স্যার নিচের পার্টটা স্যার একটু দেখা যাচ্ছে না স্যার, ওই সব নিচে চলে গেছে স্যার।
Oh my gosh.
অল্প একটু চলে গেছে স্যার, বেশি না। মানে ওই কারেন্ট স্প্লিটের যে ব্যাপারটা বলতেছিলেন স্যার, ওইটা।
I'll take a fresh one. Okay, what I was trying to say that so these are common emitter amplifier. The common emitter amplifier has a small output. This is output resistor. We have a output resistor R now, and then we are connecting this load R, right? Now here you have the output kind of the common emitter. Let's say this is I not C. Okay. Now these two basically in parallel, so part of this current will go into this R naught. So that let's call it I01, and then the part will go here I02, right? And that is our output voltage, which will be our basically I02R, right? So since part of this current goes into the unknown, this current is shared by, right, these two resistors. So you get less current in RL, right? So that reduces your voltage and the overall gain, right, to some extent. Instead, if you had got all the current into RL, so that would have given you higher gain, higher voltage, right? So that's what is achieved using this cascade configuration, the common emitter and common base, right? So now here you have RL, and this is our common emitter, and this is our common base. And as we have shown you, the common base has unity current gain. So the current here, the output current for the common emitter, and this is our output current here. Right? So it's a unity current gain. So this is the same as C, right? So whole of the current is going into here, right? So V naught is the I naught RL. So you get whole of the current. Now the common base will also have R naught, right? The output resistance. But the current here will be very small because why?
So the resistance is very high. So the resistance is very
Right.
high.
This is much larger than a small R naught. In this case, common emitter we have R naught, but here we have this R naught much larger than the small naught. As we have shown, it will be almost R naught times 1 plus bit, right? So it will at least 100 times larger, right, than this one, right? So current will reduce by 100 times at least, right? So that is how we get the whole of the current. And at the common emitter side, still you have R naught. So you expect that part of the current will flow here, right? It will flow here, but what happens here? The common base Ri is very low, right? Common base has the lowest output input resistance in the range of few ohms, right? What is it? It is about 100 kilo ohms. So if you take the ratio, right, very small fraction, negatively small fraction will flow here. So you can always ignore that. So most of the current will actually flow in common base, and that will be transferred to the output side, right? So these are what is known as the current buffer, right? Unlike the common collector, which works as a voltage of a common base, works as a current buffer. Right, and that is how it helps, right? And it modifies the gain expression for the common emitter amplifier. So common collector, we have shown in our last lecture, we add the common collector at the output of the common emitter to enhance the 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 load resistance seen by the common emitter and the gain, and make the gain independent of the load resistance. And in this case, the cascade configuration is the opposite. We are not making it independent of the load resistance, rather we are making it independent of the output resistance of the common emitter amplifier. So, and different situation, you choose the different configurations, right? So that depends on your requirement. Any question, guys? Is it all clear? Oh my, there's nothing. So we have determined the input resistance, the output resistance, input resistance, same as the input resistance of a common emitter. The output resistance is very high, and the voltage gain almost same as the common emitter, except for one difference. It's independent of the output resistance of common emitter, independent of small r naught. And okay, we didn't show this modification, right? So if you had this, you should be able to do this by yourself. You had this RAs, right? So VS. So then voltage gain here will take this expression of, okay, let's get the difference. Yes, this I don't know. This, they refuse to get erased. Okay, so this, let's use red color. So in this case, the voltage gain will be V naught by Vs, and that will be that's V naught by Vi and Vi by Vs. So V naught by Vi we have already determined here, which is minus GMRL, and this part will be Ri and Ri plus Rs, right? So that is the same for any amplifier that we have discussed. Here, the input side, the attenuation, it's Ri plus Rs. So that's the only modification you will need, and very straightforward. The current gain, what will be the current gain? Current gain, basically, we have already shown you the current I naught, right? We have, as you can see here, okay, we have on this. So current, the I naught is IC2, and IC2 is alpha IE, alpha IE2. IE2 is IC1, IC1. So that's it. So what you write here that, okay, I go back, maybe it's become clumsy. Go to our next slide. So we have this common emitter, and then we have this, and this. So that's how we can all express the different current components, and it's pretty straightforward to determine the current gain. So I start with I naught. I naught is minus IC2. IC2 is IC is IE minus alpha IE, right? Minus alpha IE2 IE2 minus alpha 2 IE2. And IE2 is same as IC1, so we write minus alpha 2 IC1. And IC1, what is IC1? IC1 is?
Beta IB.
Right, IC is beta IB. Right, IC is beta IB. So we write beta 1 IB1. Right? And in this case, IB1 is same as the input current II. So that's IB is II input current. So the current gain, current gain will be I naught by II, that is minus alpha 2 beta 1. So current gain alpha 2, if you can approximate to 1, so that reduces to minus beta 1. Right? So that is the same as what we have for the common emitter. Common emitter current gain is minus beta. So beta 1 in this case is the first transistor. So current gain also same as the current gain of the common emitter. The input resistance are same as the common emitter. Gain is also same as the common emitter, except the fact it is independent of the small r naught. And the only difference here, major difference here, is that the output resistance will get a very high output resistance. Any question, guys? Okay, we have come almost to the end of today's class. So probably we should stop here. Not enough time to go to the next and the topic. Or any question, guys?
No, sir. Sir, what will be the term question pattern?
Question pattern is a difficult question. I'm not prepared to answer that question. I have to think about that. What kind of questions we can put in the midterm? Of course, within our discussion, it will not be outside our discussion, right? And questions can include drawing the different configurations, right? If you want to increase the output resistance, or if you want to decrease the input resistance or decrease the output resistance. So how do you modify these circuits? If you are given a circuit and we ask you to modify this circuit to increase or decrease the output resistance. So how do you modify that circuit? And what we have discussed today, like how can make the gain independent of RL, or how can gain make independent of small or not, or there can be calculations, right? How do you bias the transistor in active mode? And or we can just give you a circuit and ask you to determine the voltage gain, current gains, input output resistances. Right? We can have tricky questions, and we can have conceptual questions. Any questions? So if you have good understanding and clear conception of the subject matter will be answered, so there will be no problem.
Okay, sir.
Okay, good luck, guys. That is the end of our this week, and I will see you next week. Okay, take care and Allah Hafiz.
Assalamu alaikum, sir.
Assalamu alaikum, sir.
ওয়ালাইকুম আসসালাম ফাহিম।
রেকর্ড এখনো শেষ হয়নি।
আমরা লিভ করে রেকর্ড শেষ হয়ে যাবে।